Welcome to this presentation on analyzing and designing algorithms. In this session, we aim to explore the fundamental aspects of algorithm development and evaluation. Algorithms form the backbone of computer science and are integral to solving problems efficiently. We will cover key concepts, including insertion sort, divide and conquer strategies, merge sort, and techniques for analyzing their efficiency and correctness. Through this, we hope to provide insights into how algorithms are designed and assessed for performance, ensuring they meet the demands of modern computing. Our journey begins with understanding why algorithms are essential. They enable us to translate complex real-world problems into solvable computational tasks. Whether optimizing search engines, simulating scientific phenomena, or developing artificial intelligence, algorithms are indispensable. Each step in their creation and analysis brings us closer to more robust, scalable solutions. Throughout this talk, I encourage you to think critically about the principles and methodologies we discuss. Let us begin by diving into a simple yet powerful algorithm: insertion sort. Insertion sort is one of the simplest sorting algorithms, yet it demonstrates critical principles of algorithm design. Here's how it works. Insertion sort builds a sorted array incrementally. Starting with a single element, it adds one element at a time, placing it into its correct position within the already sorted portion of the array. This process is repeated until the entire array is sorted. Let us consider an example. Imagine sorting a deck of cards in your hands. You pick one card at a time and insert it into the correct position among the sorted cards. This mirrors how insertion sort works. While simple in concept, the algorithm's efficiency depends on the input data. If the array is nearly sorted, the algorithm performs quickly. However, for unsorted data, it requires more comparisons and shifts, making its performance less optimal. Analyzing insertion sort involves examining the number of comparisons and swaps required. These operations determine the algorithm's time complexity. In the best-case scenario, when the array is already sorted, insertion sort operates in linear time, or theta, n. In the worst case, with a reverse-ordered array, it runs in quadratic time, or theta, n squared. Understanding these scenarios highlights the importance of selecting appropriate algorithms based on input characteristics. Analyzing algorithms is a crucial step in understanding their performance and suitability for specific tasks. The running time of an algorithm is a primary factor we evaluate. This is often expressed as a function of the input size, providing a clear picture of how the algorithm's performance scales with larger datasets. In particular, we focus on worst-case analysis. This involves examining the algorithm under the most challenging conditions. Worst-case scenarios provide guarantees about the upper limits of performance, which is critical in applications where reliability and predictability are paramount. For example, in systems where delays could lead to failures, knowing the worst-case performance of an algorithm ensures that we can plan accordingly. Additionally, we use the concept of order of growth to describe how an algorithm's running time increases as the input size grows. Big O notation is commonly used for this purpose, providing a standard way to compare algorithms. By analyzing these aspects, we gain a comprehensive understanding of an algorithm's behavior and can make informed choices about its use. The design of algorithms is as much an art as it is a science. Various strategies guide us in crafting solutions to computational problems. One approach is the incremental method, as demonstrated by insertion sort. By building the solution step by step, we can tackle simpler subproblems and gradually construct the complete answer. Another powerful technique is divide and conquer. This strategy involves breaking a problem into smaller, manageable subproblems. Each subproblem is solved recursively, and their solutions are combined to address the original problem. This approach is particularly effective for complex problems, as it leverages recursion and parallelism. Dynamic programming is yet another strategy. It is used when subproblems overlap and can be solved more efficiently by storing their solutions for reuse. This method avoids redundant computations, making it ideal for optimization problems such as finding the shortest path in a graph, or solving knapsack problems. These strategies exemplify how creativity and logic intersect in algorithm design. The divide and conquer method is a cornerstone of algorithm design. It follows a systematic process to break down and solve problems. The first step, divide, involves splitting the original problem into smaller subproblems. For example, in merge sort, we divide the input array into two halves. Next, we conquer by solving each subproblem recursively. These solutions are often simpler to compute because the subproblems are smaller instances of the original problem. This recursive process continues until the base cases are reached, where the problem is simple enough to solve directly. Finally, we combine the solutions of the subproblems to solve the original problem. In merge sort, this involves merging sorted subarrays into a single sorted array. The divide and conquer approach is not only elegant but also efficient, especially for problems that can be naturally divided into independent components. Merge sort is a classic example of the divide and conquer strategy in action. It works by recursively dividing an array into smaller subarrays, sorting each, and then merging them to produce a sorted array. This process continues until each subarray contains a single element, at which point it is inherently sorted. The analysis of merge sort involves understanding its recurrence relation. The total running time is determined by the time taken to divide the array, conquer the subproblems, and combine the results. For merge sort, the recurrence relation is Tn equals 2Tn/2 plus theta, n, where theta, n, accounts for the time to merge the subarrays. Solving this relation reveals that merge sort operates in theta, n log n, time, making it highly efficient for large datasets. Merge sort's consistent performance, regardless of input order, distinguishes it from algorithms like insertion sort. Its ability to handle large data efficiently makes it a preferred choice for applications requiring reliable sorting. Analyzing divide and conquer algorithms requires a structured approach to solve their recurrence relations. These relations express the total running time in terms of the time taken by recursive calls and additional work such as merging or combining results. Several techniques are used to solve these recurrences. The master theorem provides a direct way to determine the running time for common forms of recurrences. For example, it helps confirm that merge sort's running time is theta, n log n. Alternatively, recursion trees visualize the breakdown of the algorithm's execution, showing how work is distributed across recursive levels. Understanding these tools is crucial for analyzing complex algorithms. They allow us to predict performance, optimize implementations, and ensure that our solutions are both efficient and scalable. Loop invariants play a pivotal role in proving the correctness of algorithms. These are conditions that remain true throughout the execution of a loop. To establish an algorithm's correctness, we examine three key properties of its loop invariance: initialization, maintenance, and termination. Initialization ensures that the invariant holds before the loop begins. Maintenance guarantees that the invariant remains true after each iteration. Finally, termination confirms that when the loop ends, the invariant provides a basis for the algorithm's correctness. For instance, in insertion sort, the invariant states that the subarray before the current element is always sorted. By verifying these properties, we can confidently assert that the algorithm produces correct results. Pseudocode is a universal language for representing algorithms, enabling clear communication and understanding across diverse audiences. It employs standard conventions to describe algorithms without the syntactical details of specific programming languages. Indentation is used to denote block structures, while looping constructs mirror those in popular languages like C, Java, or Python. Comments, indicated by // provide insights into the logic behind specific steps. Array indexing typically uses square brackets to denote elements. These conventions ensure that pseudocode is both readable and precise, making it a powerful tool for algorithm development and documentation. Analyzing insertion sort's performance reveals insights into its efficiency across different scenarios. In the best case, when the array is already sorted, the algorithm performs theta, n, comparisons, as each element only needs to be checked once. In the worst case, with a reverse-ordered array, the algorithm performs theta, n squared, comparisons and shifts, as every element must be moved to its correct position. The average case performance, often similar to the worst case, highlights insertion sort's limitations for large datasets. However, its simplicity and efficiency for small or nearly sorted arrays make it a valuable tool in specific contexts. These performance characteristics underscore the importance of selecting algorithms suited to the task at hand. Understanding the order of growth is fundamental to algorithm analysis. It provides a framework for comparing algorithms based on their scalability. Constant time, or theta, 1, represents operations that do not depend on input size. Logarithmic time, theta, log n, arises in algorithms like binary search, where the problem size is halved at each step. Linear time, theta, n, scales directly with input size, while linearithmic time, theta, n log n, characterizes algorithms like merge sort that combine linear and logarithmic behaviors. Quadratic time, theta, n squared, as seen in insertion sort's worst case, grows rapidly with input size, making it unsuitable for large datasets. These distinctions help us evaluate and choose algorithms effectively. Merge sort's analysis demonstrates the elegance of divide and conquer algorithms. Its running time is derived from the recurrence Tn equals 2Tn/2 plus theta, n. Solving this relation reveals a total time of theta, n log n, highlighting merge sort's efficiency. The algorithm's divide and combine steps each take linear time, theta, n, while the conquer step involves recursive sorting. This balanced workload across recursive levels ensures that merge sort scales well with input size. Its predictable performance and robustness make it a go-to choice for sorting large datasets reliably. Comparing sorting algorithms provides valuable insights into their strengths and weaknesses. Insertion sort excels in small, nearly sorted datasets with a best-case time complexity of theta, n. However, its average and worst-case complexities of theta, n squared, limit its use for larger datasets. Merge sort, with consistent theta, n log n, performance across all cases, is ideal for large-scale applications. Quicksort, another popular algorithm, shares merge sort's average case performance but has a worst-case complexity of theta, n squared. By understanding these differences, we can select the most appropriate algorithm for a given problem, balancing simplicity, efficiency, and scalability. Algorithm design techniques encompass a variety of approaches to solving computational problems. Divide and conquer strategies break problems into smaller subproblems, as seen in merge sort. Dynamic programming, by reusing solutions to overlapping subproblems, offers efficient ways to solve optimization challenges. Greedy algorithms make locally optimal choices at each step, aiming for a global optimum. Backtracking explores all possibilities systematically, making it suitable for combinatorial problems like solving puzzles. These techniques, when applied judiciously, unlock the potential to address diverse and complex computational challenges effectively. Further reading expands our understanding of algorithms and their applications. Donald Knuth's The Art of Computer Programming provides a comprehensive study of algorithms, offering deep theoretical insights. Introduction to Algorithms by Corman, Leiserson, Rivest, and Stein is a widely used textbook that balances theory and practice. Stephen Skeena's Algorithm Design Manual takes a practical approach, emphasizing real-world applications. These resources, combined with hands-on experimentation and problem-solving, equip us with the knowledge and skills to design and analyze algorithms effectively. In conclusion, algorithms are the lifeblood of computer science, enabling us to tackle complex problems and optimize performance. Understanding their design and analysis is essential for developing efficient, reliable solutions. By exploring techniques like divide and conquer, dynamic programming, and greedy algorithms, we gain the tools to address diverse challenges. As we continue to innovate and push the boundaries of computation, algorithms will remain at the heart of progress, driving advancements in technology and society alike. Thank you for your attention.